In section 13.2, I'm going to discuss the physics definition of work, which is a change in a system's energy. So, work. Physicists define work as energy that is either added or removed from a system. When positive work is done, energy is added to the system, and when negative work is done on a system, energy is removed from that system. Positive physics is going to refer to negative work as loss. The units for work are the same units as energy, the joule, and work is always the result of some force being applied over some distance. So objects have to be moving, and there has to be a force applied to that object. But only forces, or the components of forces, that act in the direction of motion are going to do work. A good example or non-example of this is an object sliding across a floor. If its motion is to the right, the normal force acting on it is up. The normal force has no component in the direction of motion. Therefore, the normal force will neither add nor remove energy from the system. It will do no work. If a force acts in the direction of motion, it does positive work. It adds energy to the system. And if that force acts opposite motion, like friction, for example, then it will do negative work. It will cause a loss of energy for our system. So physicists like to define forces as either being conservative or non-conservative, and then we can address the work done by those forces. Forces that are able to change the potential energy of a system are referred to as conservative forces. And this includes gravity and elastic forces, because those are the types of potential energy that we're discussing. When conservative forces do work, they cannot change the system's total mechanical energy. And when energy is not changed, it's considered to be constant or conserved, and that's why we refer to these forces as conservative forces. The way they operate is they trade potential energy for kinetic energy. If you consider maybe a ball being thrown up into the air, as it rises, its kinetic energy decreases, but its gravitational potential energy will increase. It's a trade-off between the two types of energy. And when it falls back down, the opposite occurs, where its gravitational potential energy decreases and its kinetic energy increases. If a force can change the total mechanical energy in a system, it's referred to as a non-conservative force, because when the total mechanical energy changes, it is not constant and therefore not conserved. So everything besides gravity and elastic forces are non-conservative. So thrust, tension, applied forces are the forces that typically add energy to a system. And friction and drag, because they always act opposite motion, are typically the forces that cause a loss of energy to the system. In the next few slides, I'm going to provide you some examples that show how to identify the types of energy present in a system and how to identify whether there is work or loss of energy for the system as the system progresses, evolves. In the next few slides, I'm going to provide you with some examples that demonstrate how to identify the types of energy present in systems and to identify whether there is work and or loss occurring for a system. In this problem, we are going to consider friction and drag, and we're going to look at a roller coaster that starts from rest at point number 1 and gets lifted to point number 2 by a motor. So we'll stop there and look at the problem. Notice that there is no spring, bungee cord, nothing elastic where it's going to stretch and compress. And so in this problem, we don't have to worry about elastic potential energy. There's going to be no elastic potential energy to consider. The energy at point number 1 is going to be a total of 0. starts from rest at point number 1, so there's no kinetic energy. And point number 1 is located at the reference level, so there's no gravitational potential energy. At point number 2, the roller coaster has to be moving to get over this first drop. And so there's going to be some kinetic energy, and it's at a raised position, so we're going to have some gravitational potential energy. Look at this. We started with 0 energy. We end with some energy, so there had to be work done. The motor had added energy to the roller coaster Earth system. There was friction and there was drag, and as the car moved forward, the drag and frictional forces had to act backwards, opposite motion. So those are going to cause a loss of energy. The work had to be bigger than the loss because we ended up adding energy as a total to the system. Okay, what about point 3? Now, point 3, notice the roller coaster returns to the reference level, so the gravitational potential energy is 0. But at point number 3, it's going to be moving, right? In fact, this is going to be the fastest it's moving throughout the whole ride. So there is kinetic energy, and this is where there is lots of kinetic energy. That's where it's going to be moving the fastest. Because there's no force pushing it in the direction of motion between points 2 and 3, there's going to be no work done. There's going to be no energy added to the system. But between points 2 and 3, there is friction and drag, so the system is going to lose a little bit of energy. Point 4. Notice point 4 there is above the reference level, so there is going to be kinetic gravitational potential energy. It's also going to be moving, but it's going to be moving more slowly than at point 3. Right? When the roller coaster moves up, it slows down. So there is going to be kinetic energy, but not as much as at point 3. Again, there's no motor or any force pushing it in the direction of motion, so there's no work done, but there is friction and drag, so there will be loss. And back to point 5. Point 5, it's going to be moving, so there will be kinetic energy. It's back to the reference level, so there's no gravitational potential energy. There was no forces pushing in the direction of motion, so no work done. There will be loss between points 4 and 5. I do want to note that the kinetic energy at point 5 has to be less than the kinetic energy at point 3. Notice points 3 and 5, they're at that reference level, so they both have 0 gravitational potential energy, but from 3 to 5, there was loss the whole way, right? So the system as a whole lost some energy, so whatever kinetic energy is left at the very end at point 5 had to be less than the kinetic energy that it had in the middle. In this next example, we're going to consider a cyclist who pedals when ascending a hill, then coasting on the way back down the hill. And again, we're going to identify the energy types present in the system and whether there's loss and or work done between those positions. So again, there is no spring or elastic material, so we're not going to consider elastic potential energy at all in this system. At point 1, the cyclist is at the reference level, so there is 0 gravitational potential energy. It looks like he's probably moving a little bit, so there probably is a little bit of kinetic energy. Now, he's pedaling, which means that there is an applied force pushing up the hill, and the motion is up the hill. So that means the applied force that's provided by the cyclist is going to do work. There's going to be work added to the system. While the cyclist is moving up the hill, there's going to be friction and drag pushing downhill, and that friction and drag are going to contribute to some loss of energy. At point 2, I assume he's going to be moving a little bit, so there will be some kinetic energy. And there's also going to be gravitational potential energy. There has to be more energy at point 2 than there was at point 1. So that means that the work done by the cyclist had to be bigger than the loss of energy that occurred between points 1 and 2. Now let's consider point 3. At point 3, he's back to the reference level, so there is no gravitational potential energy. But since he's moving down, gravity is going to be converting some of that gravitational potential energy he had at point 2 into kinetic energy at point 3. We would expect the kinetic energy at point 2 to be less than the kinetic energy at point 3. Gravity is going to convert potential energy to kinetic energy. There will be no work done on the system. There is no force pushing in the direction of motion, except for gravity, but gravity is conservative. Conservative forces can't change the total energy. However, there will be friction. Friction will push uphill, so will drag as the bicyclist moves downhill. That means there's going to be loss occurring for the system. And for our last example, here we have a ball that's launched from a slingshot. We want to identify the types of energy in the slingshot ball earth system and identify any loss and or work. So to start at point 1, that's where the ball starts before it gets pulled back. So we're going to assume that it's starting from rest. And notice it starts above the reference level. So there is gravitational potential energy. But at this point, point number 1, that's where the slingshot is not stretched yet. So it has not stored up any elastic potential energy. Now, between points 1 and 2, the ball is pulled this way by some applied force as it moves in that direction. So there's a force pulling in the direction of motion, so there's going to be work done. The person pulling the slingshot back will add energy to the system. You can consider there to be loss. I'm going to say there is no loss here. There will be some drag force acting on the ball, but we're going to say that drag force is negligible from points 1 to point 2. Now, at point 2, just before the ball is released, I'm going to assume that, again, it's not moving. Again, it is above the reference level, so there is gravitational potential energy. And at this point, there's going to be elastic potential energy because we have a stretched elastic band here. Now, at point 3, this is after the ball is launched. We'll assume that it's moving. It's back to the reference level, so there's no gravitational potential energy, and there is no elastic potential energy because at this point the slingshot is no longer stretched out. So what's going on here is that the spring stores up energy. It gets released, that energy gets released into kinetic energy, and then as it falls back down, some of that gravitational potential energy turns into kinetic. So between points 2 and 3, there is no force pushing in the direction of motion, so there is no work done. Here, you could consider there to be a loss of energy due to drag force, but again, we'll say that the drag force is very small. It's a small object moving at probably not super fast speeds, so there's probably not a loss of energy. Not a significant loss anyway.